We began this course with a look at Piaget's theory of mental development as a guide to why we are going to teach things in a particular way. In Piaget's theory, intellectual development proceeds via interaction between an organism, which is the brain, and its environment. And just as an organism adapts to changes in its environment, the mind assimilates perceptual stimuli and thereby also undergoes a change. In Piaget's theory, Piaget put together a set of mental stages based on age through which children develop as they grow. Each stage is based on certain abilities to perform certain mental operations and an inability to perform others. At birth, a child is in a sensory motor stage, which doesn't really concern us here, but his behavior in this stage is mostly reflexive. It's self-centered, which means he cannot take the viewpoint of others. And he will not look for hidden objects. He doesn't believe they exist. In Piaget's model, this is the absence of an identity operator. Identity operator being like multiplying by 1. That's an identity operator. In beginning schools, children will most likely be in a pre-operational or concrete operational stage. In the pre-operational stage, children tend to center on one particular physical aspect. They can't pay attention to two things. And so we say they don't conserve certain things. As an example of the concrete operational stage, for example, children cannot put things in order. And this is because of the missing operation of transitivity. Mathematically, that would be if A is bigger than B and B is bigger than C, this implies that A is also bigger than C. But this involves basically putting things in serial order from smallest to largest. And they also cannot reverse operations. One operation cannot be annulled by another. And finally, after concrete operations, the final stage is the stage of formal operations. Right now we will not talk about that operation except state the fact that it exists. But let's look at examples of conservation or non-conservation from Piaget's theory. A child who doesn't conserve, for example, if you give that child 2 beakers of juice and then you pour one of those beakers into another beaker that's thinner so that the juice stays higher, the child will maintain that the juice in one of these is more than it was in the previous one. And so they don't conserve, we say they don't conserve amount. Similarly, if you have a number of coins and the child counts how many coins we have, 6 here, and if you separate the coins in one pile further apart and you ask the child, is there still the same amount of coins here? Children who don't conserve a number will claim that one or the other of these rows has more, and that's because they're focusing on one aspect of this problem, and that is length. They cannot pay attention to two things, number and length. Similarly here, a child in the pre-operational stage may claim that there are more elephants here than rabbits, even though they can count, and this is because they don't conserve number. They focus on size instead of number. So what factors contribute to mental development according to Piaget? Well, there's 4 of them right here. First of all, maturation, which basically is neurological growth. We don't have any control over that. The child just matures at its own pace. But the experiences that the child has with the environment, so that assimilation and accommodation that take place. In other words, the child assimilates, the child's brain assimilates various stimuli, and a result changes, accommodates. And in particular, in this theory, for this to happen, social interaction is very important. The children interact with one another, interchanging ideas. Also, another factor contributing to mental development is equilibration, which we will talk about later in the semester, but involves cognitive conflict. That is when children are placed in the position where they have to predict something, and that prediction does not predict or explain something, and that prediction or explanation does not seem to be able to is not true. They show a contradiction, and so the mind goes into a state of mental disequilibrium. So the implication of education is that our teaching should be less verbal and not abstract. In other words, children should be more actively involved, not just listening to us talk or explain. It also implies the use of concrete materials. In this course, we use manipulatives such as base-10 blocks, fraction pieces. You've already seen these. We should do experiences where children have the ability to work in groups and interact with peers. And something we'll discuss a little bit more later, the use of mental, open-ended activities, activities that don't necessarily require a correct or incorrect answer. So if children coming into first grade don't necessarily conserve numbers, some of them at least, what types of activities can we do with the children? These are what are called pre-number activities, appropriate for either kindergarten perhaps or first grade. Well, this is what this part of the review will be about. Pre-number activities will involve, first of all, classification. In other words, selecting objects according to some attributes and classifying them. In other words, making piles. Now you can things around the house, the class, or you can commercial attribute blocks, and the attribute blocks looks like this. They have different colors. Some of them are circular, some of them are triangular, some of them are square, some of them are rectangle. They also may have different sizes, different thicknesses. And for example, you can ask children to classify them, as in this case, according to red. So you put all red things in one pile, that's a classification. And you could put all round things in another pile. That's a classification. So these are all things that involve classifying things to an attribute, the attribute being red or triangular, etc., or circular. Here's a particular case where we have red and round as we did before, and which things will fall right in the center. The things that fall into the center here, to this part, have to have both attributes, both be red and round. This is called Venn diagrams. So red and round, I don't have any here, but in regular attribute blocks you could have some both red and round blocks. Here we have three circles requiring different attributes. One is red, one is circles, and one is green. And so, for example, what will fall into this area will be circles that are red. Again, we don't have any. What will fall into this area here? Well, circles that are green. And we do have some green circles over here. So we can move into this area. Right in this little small part here, we'll have both red and green things, just red and green things. So the things that could go in there, red things can go in here, green things can go in here, etc. Here's a Venn diagram activity using numbers. All things that are multiples of 5 will go into this area. So this is a multiple of 5. All of these are multiples of 5. All numbers that are even, well, all of these are even will go in here. And what will fall in the center over here? What will fall into this center area? Well, multiples of 5 that are even. So let's see, what multiples of 5 are even? Oh, here's one. Here's another. So these would fall into that area. Again, this is an example of Venn diagrams. Another procedure for pre-number activities is making a pattern and trying to figure out what comes next. So for example, if you look at the first pattern here, if you can figure out what a pattern is, and we can see that it's square, circular, triangle that are red. Here we have a square, red, green, green square, circular square. So what comes next? Well, obviously a triangle, which is green. And here are other patterns, complete what comes next activities, which you may want to try. So at this point, we move into teaching our place value number system. And from the National Council of Teachers of Mathematics, we see that we should be teaching in K to 4 the understanding of our number system, particularly group value and place value. What does that mean? Well, what that means is that in our number system, each digit of a number represents the place of the digits represents some value. So for example, this 7 here is in the first place to the right, beginning from right, and that represents how many ones there are. The 5 here is in the tens place, and that represents how many tens there are. The 3 is in the hundreds place, and the 6 is in the thousands place. Now, 1,000 is 10 cubed, 100 is 10 squared, 10 is 10 to the 1, and 1 is 10 to the 0. Matter of fact, any number raised to the 0 is 1. For example, 7 to the 0 power will be 1. So children have to understand that this is how our place value number system works, and the reason we have multiples of 10 here, each place value is 10 times the previous one, is because we have 10 different symbols, 0 to 9, that's 10 different symbols. So the way you start teaching place value is to have children group things in groups of 10 initially. So if you give them a bunch of, for example, straws, ask them to make a group of 10 and have little bins where you put a rubber band around the straws and place them in the tens bin, because whenever you have 10, and whatever is left over goes into this bin, and children then will be able to write that this is one group of 10 and 4 more left over. Ultimately, you will get numbers become bigger, and eventually you have 10 of these 10 groups of 10, and you make a big group out of that, a group of 100. So here you see another example of such bins using sticks or straws that you could put a rubber band around. So this is how we should begin teaching two-digit numbers, having students group things in tens initially and whatever is left over. Eventually they should be able to show numbers using base 10 blocks, for example. So for example, either show numbers or know what number is being shown. In this case, we have 200s, 110, and no ones left over. Eventually you go to more. What number does this show? For example, 1,000, 200s, 2 tens, and 1 left over. So this is what we mean by place value, that children know that this place represents how many ones. This place represents how many thousands. This place represents how many hundreds you have. And this place represents how many tens you have. There are different number systems, but I've addressed the different number systems in another video, the previous video. But we'll talk a little bit about the binary number system, because this is a rather important system. The binary number system uses only 2 digits, 0 and 1, to show numbers. So for example, a number like 1, 0, 1, 0, 1, 1. What number is that? Well, the place values in this number systems, this digit would show you how many ones there are. This digit will show you how many 2s. This digit how many 4s. This place tells you how many 8s. So a number like 1, 0, 1, 1 means 1, 8, no 4s, 1, 2, and 1, 1. The place values are multiples of 2, because we have just two different symbols. Just in the base 10, the place values are multiples of 10. So this number would be 8 plus 0, no 4s, 1, 2, so plus 2, plus 1, 1. So the number would be actually 11. There are only that many types of people in the world. Is this true or false? What do you think? Those who understand binary and those that don't. So this, for example, binary numbers can be written by using switches, using light bulbs. For example, light bulb could be either on, which means a 1, or off, which means a 0 in that particular position. And so this slide just shows you all the binary numbers going from 0 to 20, what they would look like. So for example, how would you write the base 10 number 12 in binary? Stop the video and see if you can answer this. To answer the question, you really need to know what the place values are. So if you have 12 objects, how many groups of 8 can you make out of that 12? Can you make one group of 8? Yeah, you can make one group of 8. How many would you have left over? Well, you would have 4 left over. Can you make a group of 4 out of that? Yes, you could. You could make one group out of 4, and you have none left over. So you can't make anything else. So coming back to the multiple choice, E would be the correct answer for this. So look at we looked at how to teach addition and subtraction of numbers, eventually leading to an algorithm. So let's review how we did that. You begin teaching addition as the joining of two sets. So for example, a set of 1 and a set of 3, you put them together, and you have 4 rabbits. Initially, these experiences should involve no borrowing or no carrying or borrowing, which means the number should add up to less than 10. You should do word problems. You could also take away things from a set. In the case of subtraction, you could use the cover-up method where you cover one number up by the other. So 7 minus 3, what's left uncovered right over here, this many blocks, is the answer to 7 minus 3. Of course, if it's 7 minus 4, then we cover one more block, and this would be the answer to 7 minus 4. You can start using the place value mat for base 10 that we've used with simple problems in addition, like showing a number like 14, which would involve 1 rod and 4 ones, and adding to that some number and showing that number. You show both numbers and then you place things together. Now when you do that, you will find you will have a group of 10 here. And so whenever you get a group of 10, you need to exchange that group for a rod, and that will give you the answer. This is called regrouping. So initially you should have simple problems like this where you have a 2-digit numbers added with a 1-digit number, initially with no regrouping, and at some point starting an example like this where you have 1 regrouping. And this proceeds to more complex problems. We show each number, 23 and 32, bring things together to see what you have. In this particular case, the first example, there's no regrouping required. You just bring things together and see what you have. In the second case, there is regrouping required, because when you bring in all the ones for 46 and 27, you bring in all the ones, you have a group of 10, which you then have to place in here. And then here we have 2 regroupings. You have to regroup twice. 162 and 59. When you bring in all the ones together, you'll have 10 right here, which you will have to regroup and exchange for another rod that you're going to place here. And when you count all these up, you will have 10 tens, which you exchange for a flat, which you will add here. As we mentioned before, subtraction can be begun by using the cover-up method. So 6 minus 5, cover one with the other. What's uncovered, which is this one block, will be the answer. Or the answer looks something like this, 6 for 6 minus 5. Of course, you can use that even with larger numbers, like 65 minus 32. You can cover these up and cover these up, and the answer is what's uncovered, which is 33. So initially the problems are fairly easy. You cover up and you see what you get. But in a problem like this, when you try to cover up, you notice that you don't have enough ones to cover up. I'm short 1 up there. So I'm trying to subtract 25 minus 16. What do I need to do? Well, I need to get more ones here, and this is where I'm going to get them from, the top here. I'm going to exchange this for 10 ones, put them over here. Oops. Five, 6, 7, 8, 9, 10. So I cover up now. I can use the cover up method here, and I cover this up also. So what's uncovered? Well, it just, everything's covered except these over here. That's the answer. In this case, the answer is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And there's nothing in the tens column here. You want to lead to an algorithm. So there's a bunch of steps that you can do to lead to an algorithm, probably in grades 5 or so. First of all, you use less concrete materials, like trading chips, and even you can use play money. So you can, but using only $100, $10, and $1 bills. So using play money, you can do the same thing. Show each quantity together, 142 plus 173, and you can add all the bills together. When you have 10 ones, you exchange it for $10 bill. When you have $10 bills, you can exchange it for a $100 bill. To get to the algorithm, by using less concrete materials, in the final step, you would take the materials away and just have your students write the number in columns like this, like 175. Write it in the column. They will sort of remember that this 5 represents the ones, that this 7 represents tens, that this 1 represents hundreds. And basically, they'll be doing mentally the manipulations with